quite a number of persons usually will drop by the wayside. And so for us to have this number still keeping up with the training sessions, I think it is something that is very commendable, which is why I'm also appreciating you for the kind of commitment that we have shown towards learning as much as possible within this frame of time in which this training program has been organized. And so on this note, I want to welcome us to another class today. Today is a follow-up to the last class that we had, and today we will essentially be talking about some common statistical analysis that many of us are used to. Maybe, even at the level of first degree and master's and even PhD, the kind of test that we want to take ourselves through today is very common and it's very relevant. I cannot even imagine if a time will ever come that we will not still be talking about these two. So they are very relevant to research. That's why it is important that we take ourselves through these classes. Now, today, like I said, we are following up on the last class, and essentially, we'll be looking at these three tests. We'll be looking at test of independence, then we'll be looking at one-way ANOVA tests, and of course, we'll look at also two-way ANOVA tests, and we're going to wrap up. We're going to wrap up. Okay, as much as possible, I will want us to follow keenly. If it's possible, we have the script already dropped in our folders, so I want us to follow through one step after the other as we run through the script. But usually, the way we have always done, what we'll do is, I'll first of all give us some background information with respect to the test, each of the tests that we are going to be talking about. I will be talking first about test of independence, after which I will talk about ANOVA. And so I'll be talking about both one-way ANOVA and two-way ANOVA together on the PowerPoint. Then we'll go to the script so that we'll see how that plays out on the R Studio. So test of independence. Yes, when we talk about test of independence, this really talks. I'm supposed to put on my video. I think that's like a rule. I just remembered now that I only enabled my audio. So my sincere apologies. Okay, so when we talk about test of independence, we are essentially talking about the kind of tests that is conducted between two categorical variables. The kind of test that is conducted to test for relationship between or to test for independence of two categorical variables. I mean, you agree with me that we have different types of variables, which we have actually talked about extensively, build up to a time like this that we are talking about this topic here. Now, categorical variables are variables that are in categories. They are in discrete form. They are in they are in nominal level. In which case, we are not talking about numbers. We are not talking about continuous. We are talking about variables that are in categories. For example, we are talking about sex. Sex can only come in categories of two, male or female. Religion can also come in a category of, in the context of Nigeria, we say, okay, Islam, Christianity, and traditional. That's another example of categorical variable. And so when we as researchers have interest in looking at whether two categorical variables show some measure of independence, of course, or yes, show some measure of independence, then that means we make use of this test that we're talking about. And an example is sex, which is male and female. And of course, we also have status, which can also be in the form of rich and poor. Of course, status can assume another level of measurement differently from what we have here. However, we're going to for the purpose of this class, we'll be talking about status in looking at just categories, rich or poor. And so these two variables, if a researcher is interested in whether there's a relationship, there is, or whether status depends on sex, for example, then this kind of analysis, this kind of test is conducted. And normally, or usually, it comes with what we refer to as a contingency table, which represents a picture of association between these two variables or otherwise. And so when you conduct a test of independence, you have what we refer to as a contingency table, which shows the distribution, which shows the counts of of the different research subjects belonging to different categories. Okay, based on the interaction of these two variables. For example, we're talking about sex and status, and so we can have male that are rich, male that are poor, female that are rich, and female that are poor. And so in this case, you have counts in each of these cells. And at the end of the day, by the time you have counts across these four cells, if you're talking about a 2x2 kind of contingency table, then you talk about this being a contingency table. That's the way a contingency table is. And at the end of the day, in order to confirm whether, because when you are conducting a test, a statistical analysis, it is not, decisions are not made at the level of descriptives. Decisions are not made at the level of just counting. Decisions are made at certain significance level, say 1%, say 5%, sometimes 10%. And so in order to decide, or yes, in order to conclude whether or not there's a significance, there's significance. Of course, in order to conclude whether or not there is dependence, okay, what is done is referred to as chi-square test. And so today, we'll be looking at chi-square as a tool for testing independence of two different categorical variables. And so I will be moving straight to our script, which I dropped much earlier than now, so that we can follow through how this is conducted. I have this outline in the script, and of course I decided to to start from this point, because the data set we are going to be making use of is not embedded in R. We are actually importing the data from a particular folder, and of course we just we are used to this. So in one step we just import this into the R Studio, and of course we continue. And so to start with, I think what we first of all do is to set our working directory. As many of us as have the script, I expect every one of us to already have the script with us. We set our working directory to be sure that we are working on the folder that we actually intend to use for this analysis, in which case all our works, our analysis, every activity that is done here, of course, goes into that directory. So we set working directory from my part, from my end here, I've just done mine. And I also want to implore us to library this package, Agricola. Okay, anyone who doesn't have this installed on his or her system would like to just install. Of course, we understand how installation is done. Then you put it in inverted comma, Agricola A, I think so. Then you press your control and you enter, so that it can run. Then we can then live. So how do we import? Now the data set we want to make use of is inside my working directory here. Let me show us. Okay, let me just so that it's easy for me to navigate. I think I have so much open on my system. Okay, let me close this. Okay. Okay. All right. So the data set I'm making use of is inside my folder. Okay. And of course it's a CSV file. And so what I'm doing here is just to read the CSV file into R. And so this is the name of the file. Okay, I think I should have dropped this. I'm just remembering now. I should have dropped this in our folder as well. So I'm sending it to us right away. Okay, yeah. So like I said, we have the data set to be this. Okay, but we are trying to read it into R and we are naming it, we are giving it this name. It could either be, it can either be equal sign or this. I decided to use equal sign this time around almost throughout. Okay, so you read, and of course it shows, it reads into R. Let me start all over. Okay. 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 I think I made a mistake there. Now, so the name of the object is income. INC. The data set from my working directory is income data, and that's exactly what you should also have downloaded. So, reading it, you have it. Then for the structure, sorry, something's running. My R, I think, is going to restart. So what I'm running now is not it's not executing. So just kindly give us 2 minutes. Okay, I think it's back now. Okay. So this is the structure data. So you have about 521 observations. That's like 521 rows and 10 variables. And we have these variables: income, education, not, experience, sex, member, age, occupation, sector, and married. And if you look at all of this, looking at this, this is numeric. Income is numeric, education is integer, not is integer as well. Experience is integer, sex is character, this is integer. So you have this. Now, yeah, I think we should just go on to the studio. I think it's important that we have that kind of knowledge. Now, if for a chi-square analysis, because we are talking about two variables that are measured at that are categorical, and so it's important that we bring the variables of interest, especially the variables we want to use to run the test, to bring them to factor level. And so what I have done here is to have selected some variables of interest, of course, the variables in categorical form, and of course, convert them from whichever format they are into factor. And I think that this has been done way before now. So income, dollar sign not, is converted to factor. So using as the factor, yeah. So this is the command. The same thing for sex, the same thing for member, the same thing for occupation, the same thing for sector, and the same for married. And so if you run all of this, because if you look at married is in integer form, 110100101. So it's supposed to be converted to factor, and that's exactly what we have done. So this is converted into factor, factor. Okay. And so by the time you do the structure again, to see if exactly they have been converted, you discover that those variables have actually been converted into factor. It's important that they are converted into factor, otherwise R may mistake in them for either a continuous variable or an integer. So, and that's why we needed to have done that. Now, we should also note that some factor variables are coded numerically, and this is easier, of course, to see with binary variables. For example, if we have sex here, and once you have 1 2 1 2 1 2, of course, you know female is 1 and male is 2 based on this structure here. And of course, for married, you know that, okay, if you are 0, you are married, and if you are 1, if you are 1, if you are 0, you are married, and if you are 1, you are married. Okay. Now, however, for some variables that may be at 3 levels, for example, we look at sector. Sector is in 3 levels. Sector here, 3 levels: 0 1 2 2 2 2 1, and so on and so forth. And so this is in 3 levels. It's difficult to know exactly what 0 stands for, what 1 stands for, and what 2 stands for. Unlike for married, I can know that okay, once is 0 is unmarried, and once is 1 is married. So for a sector, it's important to define what each value exactly represents, and that's exactly what we have done here. And so what we can do is to just, when you say levels, this command gives you how many levels to each of the variables. For example, sector has 3 levels, sex has 2 levels, male and female. And so you may not bother defining any further. For sex, for not, yes, you may do this, you may not, because when you say not, this is already taking a position. And so you know that once you have 0, it's not. And when you have 1, and so you can easily understand this as you run your analysis. This is not expected to cause any confusion. However, if you want to be sure you are not making any mistake, you can still go ahead and do something like this to say that, okay, yes, 0 will be not. 0 will be not. Okay, 0 will be not, yeah, not, and of course 1 will be not. Okay. And so now you have levels, not, and not. After on, you have levels, not, and not. Okay. Now for sector is in 3 levels. Okay. What you do is originally it's in this level is 0, 1, 2. But you need to define your 0, your 1, your 2, such that when you continue to run your analysis, it will be easy for you to be able to interpret. And so, and that's why we are trying to use this command to say, okay, order is for 0, manufacturing is for 1, and of course, construction is 2, is represented by 2. That's assigned. Then, of course, you can say, okay, what do you have now? Okay, you can say levels sector, levels in INC sector. Okay, you know that you have these levels now. And of course, you want to do count. You want to count per category. You table and you index your variable of interest into the data set, which is INC, and it gives you the count per the different categories that you have within that particular variable. You can summarize to say, okay, the entire data set, you want to have it summarized, or you want to select a particular variable, okay, of interest. Say, okay, what are the entries to that particular variable? These are just introductory activities that we need to do to possibly position our data in such a manner that will be easy for us to relate with without any form of confusion at any point in time. So we are moving gradually to what we have to do for today, especially in respect of test of independence. Okay. Okay, yeah, I think all of this we've done before. So let's go to chi-square test of association or chi-square test of independence. What chi-square does is to test the association between 2 categorical variables. And of course, for example, in the data set that we have, that we are making use of, we can look at whether there's significant relationship between sex and occupation. The reason we are looking at these 2 is because the 2 of them are at categorical level, and of course, they satisfy the condition for making use of chi-square. And so how do we do this? Okay, you do this by, first of all, coming up with your count in the form of, in your contingency table, generate a contingency table. And the command for that is table. This is your variable, your data set, the first variable, and of course, your data set again, the second variable. And so you can name it, you can give it a name as an object. Okay, so that's your contingency table. So subsequently, you could say table 1, okay, tab 1. Okay. Now, you can also add the margins. Of course, you can add along the columns and also add along the rows, along the columns and across the rows. And that is what this command is going to do. For those of us that are used to manual computation of contingency table, this is exactly what is done. You see that what we have here is the total of all the respondents that we have, all the cases that we have in the data set. And so when you had like this, and you also had like this, everything must be equal to 521, whether vertically or horizontally. Okay. Now, the next thing is to do a proportion table. Proportion table is not necessarily the same thing as the count table. Proportion table gives you an idea of the distribution, how one category is represented compared to the other in the form of what looks like a standard unit percentage. And so you can do something like this. And so if you have this, what it has done is to give you an idea of the percentage that is represented, the percentage that is ascribed or that is assigned to each of the categories in the contingency table. Each category stands, is represented by a cell. And so you have the percentages that is used to represent each of the cells. So you have this as 14.5%. You have this as 3.98%. This is 5.6. This 9.6. This 3.2. This as the case may be. So now the next one is you want to also run percentage within female, percentage of occupations. Okay, these different occupations within only female. Okay, or only male. Okay, meaning across the rows, and that is what this has done. And so by the time you look at this, within female alone should be equal to 100. If you add up all of these, everything should give, should be equal to 1, which is 100%. The same thing is for male. Everything is, and so such that you could say, okay, for female, you want to see the percentage that is clerical, and the percentage that is management, percentage that is order, percentage that is professional, relative to sales, relative to service. You can do that also within male. Okay, so the first is to do proportion table across the rows. We can also do same for columns. And so all of this is just to give us an idea of how the distribution is, such that at the end of the day, by the time we are able to establish a significant relationship in our chi-square analysis, we'll have an idea of the distribution. And of course, this helps us to interpret our results. And that is the reason we are trying to, all of these are necessary. And so the second one is you want to do it across the columns. For example, you want to do it for clerical alone. What percentage of male relative to female belong to clerical? What percentage of female relative to male belongs to management? What percentage of male relative to female? And if you sum up down, you discover that this is 100%, this is 100%, down is 100%, down is 100%, down here is also 100%, just like this as well. But all of these are just to give us like what looks like an idea of the direction of the association. Okay, what helps our decision about whether or not there's a test of association is not all of this. It's still the chi-square test that we are going to be doing much later. But all of these are equally important for us to be able to interpret our results and interpret it appropriately. Okay. You may want to do a bar plot. Okay. For example, for tab 1, this is our tab 1. But that's looking at sex and occupation, relationship between sex and occupation. Looking at the bar plot. This bar plot shows, okay, we have not included the legend here, so that I think we should include the legend. Legend is true. Okay, so this gives us a clearer picture of the distribution. We can see that, okay, female are more here as clerical workers. They are male, but okay, I think we can zoom it. Okay, yes, okay, yeah, we can see here that we have more female, more female as clerical workers than male. We have less female here in management than female, and we have more male here in others category than female. Here is almost equal, professionals, and we have more male in sales than we have female. And we also have more females in service than we have the male. All of this is giving us an idea, like an understanding that possibly there's a relationship. Okay, but it is not sufficient. We want to move this. Okay. Okay. Yeah, we are. I mean, this is just to shift words. You can make it bottom right, you can make it left, you can make it right. Yeah. So, but we don't want to believe. I mean, to trouble ourselves with this. We don't want to allow that to consume our time today. There's no such time. So now, let's go straight to now the test of significance. That's statistical significance, to test whether there's a statistical significant relationship or association between sex and as an occupation. We have these assumptions. Observations are independent, and there is no expected frequencies are less than 5. So by the time we our contingency table, we generate our contingency table for expected frequency, then we should not have any frequency less than 5. If we have any frequency less than 5, then we may resort to another test. I mean, like a variance of chi-square. When we get there, I'll show us how. I mean, how this is determined. So we have this. Okay, this shows that there is actually a significant relationship. I think it shows that there's a significant relationship between sex and occupation. There's a significant relationship because that's what our tab 1 is talking about. We can actually, instead of saying tab 1, this is what we have here, and bring it down. Okay, and bring it here. Still the same thing. Go on, the same thing. But because we have named this operation, this command, as an object earlier, that's why we are imputing it here. So let me go back to what we have here originally. So we have chi-square test, expected frequencies, and so we discovered that there is no frequency here that is less than 5. So it's a good test. It fulfills that assumption for a chi-square test of association to be carried out. Now, another one that possibly we may want to look at is to see relationship between sector and membership. Relationship between sector and membership. And so we have levels for membership. We have non-member and member. Of course, we have the class is a factor, so we are good to go. We have table, contingency table for the 2 variables, sector first, then member second. Anyone can come first. It's about association, not like, it's about association. Okay. Then you have this, tab 2, that's our contingency table. Just like we did for the earlier exercise for the one we did earlier. Then we have chi-square here. Then R is giving us a warning saying that chi-square approximation may be incorrect. Chi-square approximation may be incorrect. And so it suggests that we have one assumption, at least this test failing at least one of the assumptions. And so let's look at what assumptions this is failing. One thing we can do is to do let's look at expected frequencies and see whether we know that the 2 of them are independent, of course. But here, maybe the second, let's look at the second assumption that says that the expected frequency must not be less than 5. And so we can run this using this command to check expected frequency assumption. Okay, so by the time you see it, you discover that yes, when we look at this, you look at this. Okay, this less than 5, and that's why the warning came up. And so instead of doing chi-square analysis, we can do Fisher test, which is like a variant of chi-square. It runs almost exactly like chi-square. The only difference is that this can work for any scenario whereby we have an unexpected frequency. Expected frequency of less than 5. So it runs perfectly. Runs perfectly. And if you look at what was obtained when we ran chi-square, which is 0.082, and now when we run the Fisher tests, we have 0.084 or 85. It's close, but the writing is expected to be done, so it's very close. But the only thing is chi-square is not appropriate because it does not fulfill that assumption. So that's why we resorted to the Fisher test. But in all, at least from the two analyses, we can see that it is not significant. I mean, this is greater than 0.05. It's only if you are operating at 0.1, which is not really a very popular approach. I mean, a very popular decision criteria for this kind of analysis. So the two is not significant. That's about that. So we can use this to run any form of analysis if our interest is in looking at association between two variables that are measured at categorical level, that are measured at nominal level, that are measured at discrete level, that are not continuous. We want to see a test of independence, a test of dependence. We want to see whether the one depends on the other. Then we can choose to run chi-square analysis. Before we go to ANOVA, I want to welcome anyone who possibly has any question.
Yes. Hello, sir. Hello, can you hear me, sir?
Yes, you have the floor. Thank you.
Yeah. The question I want to ask is that for us to be able to run this ANOVA and all the parameters we want to run for today, is it that they are all embedded in the the software we first of all downloaded, the Argo lay? So without we having that, we'll not be able to run all this analysis on our app.
Oh, okay. Yeah. Agricoli is just a package that you will be needing for your ANOVA. We have not even gotten to that part yet. And even for the ANOVA, I think it's only that part that has to do with post-hoc when you need to do separation of means. That's when Agricoli is actually necessary. The reason I asked us to library it earlier was because for the class, it is the only package that we will need to library, and I wanted to use that as an opportunity to get us prepared for the class. I was also going to mention that by the time we get to where exactly that package will be necessary, will be needed. But it's a good one that we were able to ask the question. So we've not made use of that package yet, yeah, especially for this part, but we'll be needing it in the next phase of our analysis that we are entering into. Thank you.
Second question, sir. Can I ask a question?
Yes, you have the floor, please. Thank you.
I'm still asking a question, please. I'm still asking, please.
Okay.
I have a second question. From the result we have,
please. Hello, please. If you have any question, please just ask all the questions so that we answer you, then another person comes on board. Yeah, thank you. If you have like two questions now, you can answer them together. Yeah, thank you.
Okay. So the last question is the result we got from the chi-square. It's saying x square is 92 point something and df is equal to 5. Now, those of us that are novice in the statistical estimate, we need some little explanation. Now we will know the significance of those values. Thank you.
Okay. Let me take you to the results. Okay, yes. When you run a chi-square analysis, you have chi-square value. Okay, and you have your degree of freedom. I want to believe we have an understanding of what a degree of freedom is. And for chi-square, you know that all of the analysis that you run has a formula for computing your degree of freedom, whether ANOVA, whether correlation, whether t-test, independent, paired, as the case may be. In this case, in the case of ANOVA, because we are dealing with a 2x2 contingency table, for chi-square, the formula for degree of freedom is C minus 1 in bracket, then R minus 1 in bracket. C stands for column and R stands for row. And so because you have two rows, that's 2 minus 1. Okay, 2 minus 1. Then the second one is 3 minus 1. That's the sector. 3 minus 1. So if 1 is the first, the one in the bracket, the result of the first one in the bracket, and 2 is the result of the second one in the bracket. So you multiply the two. 2 multiplied by 1 gives you 2. That's why you have 2 here. That's your degree of freedom. But all of these really do not count in your decision. What counts in your decision is this value, which is which you have to match against your compare against your significance level. And the decision rule is this must not be less. I mean, once this is higher than 0.05, then the decision is that it is not significant. Or if it's within, if it's lower, then it is significant. And this is your chi-square value. Most times you have your chi-square value getting big when you have it significant. You have it insignificant here, and that's the reason why you have it low here. I may not really know, I may not be able to explain better than that. But when you have an analysis like this, deal more with your what's it called, with your p value. Yeah. Okay. Thank you.
Hello, sir.
Yeah. Okay.
Yes, sir. I would like to ask about the test on dependency. Is it only used for categorical variables? I'm only use it for them.
Yes, you use it for categorical variable. You use it for categorical variable. Yeah.
So we cannot use it for variables like integers.
No. When you are talking about integers, you are talking about continuous variables. You possibly would most likely be talking about another test entirely. So it depends on exactly what you want to achieve. If you are looking at if you are looking at association still, but then the variables you have are integers. Maybe the two of them are integers. You want to consider correlation, or you want to consider Spearman rule, depending on the kind of variable you are dealing with. However, if you are dealing with two variables and one is categorical and the other is continuous, then you have a problem. And the problem is, how do you do this? Okay, you may want to consider t-test, but you want to also be sure that that is also consistent with, it's not violating the assumptions of t-test analysis. And so you may just want to say, okay, one of the variables that is at continuous level, you can, for example, use ifs function to just categorize it into two, to say, okay, this, I can also take this also to categorical variable. For example, height can range between income can range between 1,000 and 100,000 in your data set. A variable in your data set, income, can have that kind of range. And so you may want to use a certain criteria to say, okay, if you fall below this income range, you are a low income earner. And if you fall between this range and above, this value and above, you are a high income earner. And so at the end of the day, you have been able to bring a continuous variable or an integer. You have been able to reduce it to a lower level of measurement, which is now nominal. We are now dealing with a categorical variable. So in that case, you can still make use of this tool. So before you can talk about chi-square analysis at all, you will see that if you are dealing with a categorical table, you will not be able to make any sense. I mean, a continuous variable in this kind of analysis, you will not be able to make any sense of it. How you want to imagine how your contingency table would look like, for example. So it will just be so long, and you'll not be able to make any sense of it. The only reason it's easy for us to manage this data is because, and even if you are talking about, in fact, we have even some situations that you could have different categories. You could have categories numbering up to 10. That kind of scenario is also another very difficult scenario, in that even though, I mean, you want to say it does not violate the assumption that it has to be it has to be categorical, but then you have a very long list of categories, so you need to make sense of your data. And so sometimes you need to possibly process that long list of categories further to bring them to lower number of categories. For example, 10 categories too much, you can bring it to 3, depending on the kind of, the criteria you may want to use as a researcher to do that, just because you want to make sense of that data. And so I think that's the answer I want to give to that question. Thank you.
Yes, sir. Thank you, sir.
Yeah, you're welcome.
Okay, sir.
Okay.
Sir. Okay, yes.
Sorry. The last question for this session.
Okay, so I want to ask about this Fisher's exact test. Okay. Is the assumption that one of the expected values must be below 5, or
Exactly.
if okay, so you can use it if all the values
must be greater than 5.
okay, I thought it should be less than.
It must be greater than 5 for you to consider chi-square. But if it's less than, then you use Fisher test.
Okay, my question is that can Fisher's exact test be also used when the expected values are all greater than about 5? Can it be
No,
considered?
no, it's chi-square. It's chi-square you make use of at that point.
Okay, okay. Thank you, sir.
Yeah, you're welcome. Okay, so I think we have to move on. So let me locate my PowerPoint. Yes, the next point we'll be looking at is ANOVA. Okay, okay, this is an example of contingency. I didn't show this before we move to the bigger, the scripts. Okay, so ANOVA. Now, ANOVA is another very interesting topic, and of course, some people will say it tests for difference, others will say it tests for relationship. It depends on how you are trying to interpret exactly what is being done. You can use the two terminologies. So, for example, ANOVA has been defined to be used to test relationship between two variables. Two variables. But when you are testing relationship between two variables, one must be continuous and the other must be factor. And so essentially what you are doing is you are comparing the means of the two groups of that factor variable. Let me give an example. You are interested in determining the relationship between marital status and academic performance in school. Whether those who are married, those who are not married, and those who are single are doing better. Yeah, that may not really be a good one. I think it is. So you may want to do that. And when you, of course, you know that marital status can be like as much as 3 categories: married, single, divorced. And so you want to see whether that has anything to do with academic performance. And so marital status is your factor variable, and your academic performance is now your continuous variable. And so when you are doing that, what you make use of is ANOVA. And you can also say that what you are doing is you are looking at a test of significant difference, okay, among the different marital status categories that we have. Say, okay, married are different from single, and single are different from divorced, by using a particular test variable, which in this case is academic performance. So when you are dealing with that kind of study or analysis scenario or data scenario, you make use of ANOVA. That's as it applies to socioeconomic studies. We have ANOVA being used very extensively across different disciplines. I mean, it's so relevant, especially those who do laboratory-based analysis, studies, uh, different kinds of designs like RC, BD, even RCT, as the case may be. All of these designs make use of either one-way ANOVA or two-way ANOVA. And so one-way ANOVA has only one factor variable. However, when you have more than one factor variable, a test of interaction of the two factor variables is also tested or is also conducted in addition to the difference in the mean of the two groups of each variable. We are going to operationalize all of this as we progress in the course of the class. And we have some assumptions that ANOVA test must also obey. And those assumptions are that, it's one for any firm. Okay, ANOVA can only be conducted if there is no relationship between subjects in a sample. And this means that we should be talking about independent samples. The samples that we are talking about must be independent. You cannot be talking about samples that are dependent. And so in the example I gave the other time, you cannot be married and at the same time be single. You cannot be single and at the same time be divorced. You are one. So one is not in the other. And so the different groups must have equal sample sizes. ANOVA can only be conducted if the dependent variable is normally distributed, so that the middle scores are most frequent and extreme scores are least frequent. And population variances must be equal. Homogeneity of variance means that the deviation of scores. These are just reminders to many of the things we already know. We may not really pay so much attention to these assumptions in our analysis. What we just focus our activities on our attention on today is how to run an ANOVA analysis and how such an analysis is interpreted because of the time, particularly. We have some examples of ANOVA, either one-way ANOVA. For a one-way ANOVA, an example could be testing a therapeutic intervention. It could be CBT, medication, placebo, on the incidence of depression in the clinical sample. Based on the explanation I've made of what ANOVA is used to do, what ANOVA helps a researcher to achieve. Okay, and this example I've given here, I want to ask us, anyone, which is the factor variable here and which is the continuous variable in this example. I'm giving the second example, and I want another person to take note of which one is the factor variable and which one is the test variable. Testing the effect of fertilizer type on yield. So in this second example as well, which is the test variable, which is the continuous variable and which is the factor variable? Which variable are we testing? Okay, anyone?
For the first one, I think depression is the continuous variable, while the therapeutic intervention, which are the CBT, medication, and placebo, are the factor variable.
Exactly. I think that's fine. That's very excellent. The man sounded so confident. Okay. Yeah. The second one, which is
yes, for the second one.
Okay.
Okay, yes, the effects of fertilizer type, that is the NPK urea, that is the factor variable, and why the yield is the continuous variable.
Exactly. So why the yield is the continuous variable. So at this point, I think we should begin to have an idea of how our results will look like before we go straight into conducting this analysis. For example, in the first one, what we want to do essentially is to say, how do the means of these three categories compare? The means of their depression, how do they compare? Which one is bigger? Is it CBT that is bigger? Is it medication that is bigger than biggest? Is it placebo? How do they rank? Which one is the highest? Which one is the least? That's exactly what this study wants to look at. Then the second one is possibly looking at testing NPK urea to see the effect on yield. And essentially, what you want to do as a researcher here is you want to see the average yield of NPK compared to the average yield of urea. Let me say something here that the second example here, I think a test is more suitable. A test other than ANOVA is more suitable for this test that we are not mentioning today. And that's t-test. We call it independent sample t-test. It's more appropriate. Independent sample t-test is more appropriate for two groups. Okay. ANOVA is appropriate when you are dealing with more than two groups. However, it doesn't mean that it cannot handle even two groups. It will handle it just like t-test will handle it. But ANOVA, when you make use of ANOVA for t-test, more like you're underutilizing that tool. So you want to make use of t-test because it's the most appropriate for that kind of scenario. Yes, we have two-way ANOVA, in which case we are talking about two variables, two factor variables. And an example is testing a therapeutic intervention like CBT, medication, placebo, and types of exercise. That's another factor variable. When you say types, this also implying categories, types of exercise on incidence of depression. So the two factors are therapeutic intervention 1, then types of exercise 2. We are using it to test depression in a clinical sample. Okay. Now, for the second example, you are testing the effect of fertilizer type and plant density on yield of maize. You're interested in testing the effect of fertilizer type that can be NPK, urea, and plant density, maybe area of high, area of moderate, and area of low plant density. And you want to see how fertilizer type affects maize, yield of maize, plant density affects yield of maize, or even the interaction of these two factors. The interaction, for example, NPK used in high plant density location, did it produce higher yield compared to others? And so you are not looking at each of these factors alone. You are also in isolation of the other. Of course, you are doing factor, you are doing for factor 1, you are doing for factor 2, but then you are also looking at the interaction of these factors. Another example could be testing the effect of cash transfer and gender on food security. Cash transfer can be measured using two categories of yes, I'm a beneficiary. I'm not a beneficiary. That's factor. Gender, male and female. So we're interested here in those who are beneficiaries that are male, those who are beneficiaries that are female, those who are not beneficiaries that are male, those who are not beneficiaries that are female. How do they rank? Okay, which one is high, which one is low? How do they rank? To the point that you can say, okay, at the end of the day, we can conclude that cash transfer is actually effective. Okay, yeah, in improving, getting households to improve their food insecurity. So let's go into let's go into the script so that we see how this is done exactly. So before I start with the script, do we have anyone has any question on this? Anyone?
Yes, I have a question.
Okay.
Okay, like the third example you gave, when we talk about the effect of cash transfer and gender on food security, those two factors, I think they were categorical.
Exactly.
That food security, must it be continuous variable? Because I think food security there can also be factor, whether they are food secure or not food secure. Is it possible to have every one of them, both the factor and the other one, to all be categorical, or one of them must be continuous, like we have for
Okay.
previous ones?
Okay, yeah, thank you. I will answer the question now. When you want to run an ANOVA, a test of analysis of variance, one, you must have a continuous variable, because what you are doing is essentially to compare the mean. And if it's about comparing the mean of a particular variable, it is the mean of the continuous variable that you want to compare for the groups within a particular factor variable. And so it must satisfy that condition of at least having a variable that is continuous and another one that is factor. So if you are dealing with one way and over, one must be continuous and the other one must be factor. Now, in the case of food security, you can have it measured in different. I mean, the way food security is normally measured is not even food secure, food insecure. You would have first of all measured it at a higher level, maybe generating an index of food security. It could be per capita expenditure. It could be food use. You can use another. I mean, different scales to measure food insecurity. In which case, at the end of the day, each scale gives you food security measure along a continuum of score, which is continuous. And so, food security can then, for the purpose of summarizing that data, okay, you can then possibly use it to categorize your respondents into food secure, food insecure. Yeah, it is after it must have been processed for that. Yeah.
So, sir, conclusively, so it means that if the factors are categorical somehow, we must ensure that the other one we are comparing them with is supposed to be in the continuous form.
Factors must be categorical.
Then there must be more continuous.
There must be a continuous variable. If it's not
Variable.
continuous, we cannot use ANOVA.
It's clear now.
Yeah. Thank you.
So,
Okay.
so yes, please. In the assumptions for ANOVA, most times, just as you said, like we may not focus on the assumptions. Most times, find out that in most researches they don't so much look into those assumptions to ensure they're all followed. Like all those homogeneity, homosexuality. I don't know why is it always the case that we don't always try to follow those assumptions word for word, like to try to be sure everything's followed before trying out ANOVA.
Yeah, I think you are very correct. We have so many persons trying to pretend as if that those assumptions don't exist. It's not just your observation. It's also something I've personally also observed over time. However, that does not remove the fact that those assumptions and us as researchers making sure we are conscious of those assumptions and so allow them to guide our decision. I think is very, very important. For some journals, for example, I mean, as scholars want to publish papers, want to inform policies. Some journals that are good, I mean, high impact journals, in the SCT of this world, the Taylor and Francis, all these big journals, so many of their editors will not in any way overlook this assumption. So if you want to publish in some of these journals, it's important that these assumptions are well taken into cognizance as you conduct your research. Otherwise, it's about just local journals, many of them who may not also, I mean, I would not want to say so much in that direction, but I think it's important that we take note of these assumptions and we allow them to guide our activities and decisions as we run our analysis. Unfortunately, even in this class, just like I said, I could have also taken us through how to determine whether or not some scenarios agree or violate some of these assumptions. But for the purpose of time, we may not be able to do that. We may have to consider that for another time. Maybe. So apologies for that sincerely. So let me continue. Okay, yeah, ANOVA, yeah, one way ANOVA, yeah. Like I said, what we are testing is that the group means are equal. We are testing the null hypothesis that there are no significant difference in the mean of the groups within a particular factor variable. And you have an alternate hypothesis to say at least means of two groups are not equal. Okay, so like I said, we are testing the relationship between continuous and categorical variable. You are testing if the means are significantly different between levels of the categorical variable. For example, income and occupation. In this case, your income is your test variable, is your continuous variable, and your occupation is your categorical variable. So in the data set that we're making use of today, we have income and occupation. Let's do a box plot to see how they possibly rank, how they compare. Okay, we can see some standing tall and some almost touching the baseline. Yeah. Okay, let me zoom it. Let's see. It gets zoomed. Yeah. So this is the box plot. Yeah, you can see that yes, from this box plot alone, we have an idea of how they will rank at the end of the day. So we have management and professionals. Any far more, perhaps than sales, than others, than clerical. And I think service is earning least, maybe, but it's not also significant. It's not so significantly different from at least at surface level. This is not sufficient for us to draw, to draw any conclusion or to make a decision about significance or significant difference. We have to run an ANOVA. And so this is how to run an ANOVA test. This is the function. This is the code, ANOVA function. More like if you want to run a regression. You want to run a regression, a simple regression. This is what you do. This is your code. Yeah. This code that I highlighted is your simple linear regression. But you know there is a way some of these tests are also interrelated. So in this case, just produce the ANOVA of that regression. Okay, of that regression. So you're saying ANOVA of LM lim. Okay, and so it gives you. So to make it, so there's a significant difference. Okay, or use this function. Use this function AOV. I say income against occupation, and your data is INC. You're wrong. Okay. Or you can name it, say ANOVA equals, and so you summarize your ANOVA. It's still the same thing. I hope nobody's confused. Okay. Income occupation. So I don't need this another repetition, so it's not required. Okay. So you can also do box plots for income and sector. You can see that we have outliers here. So if you are doing this kind of analysis, you know how to treat outlier cases in R. So these are you need possibly to process a data like this further, especially the income. Okay, it does appear like we may not be able to determine here anyways, because it appears like it's within categories that you seem to have these outliers. So I think we may not really bother so much about that. So we're interested in income and sector, and we can see here that they are almost at the same level. They're almost at the same level. So let's go. That gives us an idea of what we might want to expect, that there might not be any significant relationship between income and sector. And of course, there's no significant relationship. we have our P to be 0.327. Our P to be 0.327. Okay. I don't want to bother myself with all of this. There's a way you calculate all of this. But this is what is most important in our decision. Is it less than or equal? I mean, is it less than or greater than 0.05? That's what helps our decision. And for the purpose of our time, I think it's important to just move ahead. Now, yes, another one is ANOVA. You want to do ANOVA to look at income and sex. Okay, that's another one. In this case, it's significant. Even at what percent? It's significant at 0%. 0%. Yeah. So you have 3 stacks. It's significant that if you have 2 stacks, it's significant at 0.01%. That's about 0.1%. So I mean 0.001. That's about 0.1. Yeah, I think I'm correct. It's 0.1. Yeah. Okay. So let's continue. Now you need to, because it's now significant. It's important to conduct a further test, because to just say significant, you may not be able to know exactly, especially if you are dealing with 3 categories. Even these 2 categories, you want to see which one is higher than the other. And that's why there's a need to do a separation of means. We have different types of post-hoc tests that is used to separate the means in order to give us an idea of the magnitude in which they appear. However, I think we can do LSD test in R using this function. LSD is just one. We have Gonferroni, we have Tukey, we have Chefe, we have Duncan, we have different types of post-hoc analysis. So LSD is very simple and of course easy to interpret. So you could do LSD. This is my object, and this is the function LSD.test. And what do? You are saying for the ANOVA that was done earlier here, conduct a separation of means by sex. You want to see the mean of male and the means of female. Okay, conduct that, do that by text by sex. And that's what we are saying here. Maybe I did not library my agricola. Yes, I think, yeah. So there's a need for me to have library my agricola. Here I was supposed to library it here. Okay. So, and that's why it did not run. It's saying it could not find lsd.text. So I needed to come and library the package for me to be able to run that particular text. So lsd. Okay. Yeah, now it's run. Okay, so you can see now we have mean for male is 9.72 and that of female is 7.54. You have it here. You have also here. You have it here as well. You have artificial LSD here, which is the decision will be at 0.05 for our separation of means. And so you can say at 0.05 here, because these are carrying different superscript, they are carrying different alphabets. That means they are not homogeneous subgroup, groups. That means one is greater than the other. So in this case, we will know that for male is higher than female. That means men earn significantly higher level of income than their women or their female counterparts. That's that test. Now you want to print that variable. You want to save it as a doc, a DOC file format in your working directory. You can use this function. And that means what you have here, everything you have here. You want to export it. Okay. You want to export it into your working directory without having to screen grab and be saving and be saving and save. So you want to name it this ANOVA INC DOC, or you say ANOVA income 6. Okay, you sync. And I'm saying in this form, in this file, print the summary of the ANOVA. Print it, this one. This ANOVA that was run earlier that we saw. You are saying it should be printed. And you're also saying print the separation of means as well. This one, print it, the LSD that was also done. Then you're saying sync now. So when it syncs, you'll be able to locate the file in your working directory. So this is ANOVA income 6. If we check our working directory, we should be able to see it there. What's our working directory? Okay, is it there? Yes, this is the file here. This is the file here. You can open, you'll be able to see the file. But the time is really not sufficient. I think we should just move on. So this is the file. Yeah. So okay, this is it. This is it. Yeah, everything is exported. So you could do several of them and get them exported straight up to your working directory. That is the script. Okay. Now, in a way that you easily just locate and you possibly will not have any reason to be looking for any particular time. So let's go straight to the second ANOVA. That's the two-way ANOVA. Talking about two-factor ANOVA, two-factor variables and one continuous variable. So it tests the continuous variable across two categorical variables. Three hypotheses are tested here. Means the first one is means of two groups of one factor variable are the same. The second one is means of two groups of the other factor variable are the same. The third one is two factor variables do not interact. Two factor variables do not interact. That is, they don't interact. Because if they interact, the effect of their interaction will be seen in the outcome variable. And so we want to see whether their interaction, whether there is any significant difference based on the different dimensions of their interaction, the different options to their interaction. So that's what this third hypothesis is talking about. In order to be sure everybody is getting exactly what I meant here, I'm sure many of us are not hearing this for the first time. It's like refreshing our memories. I believe some of us can even do better than what I've done in terms of explaining this part. So can somebody just help us to say this in using some other words that I've used to capture exactly the same thing that I've captured, especially that's hypothesis 3. Yeah, somebody to help us. I hope nobody's sleeping.
Yeah, yes, I do. It's a bit complex.
It's not complex. It's not complex. I'm not looking for somebody like you. I'm looking for somebody who knows that it's so simple. Don't make it look like it's complex for every other person. Okay, so I want to call some people. Can I call? Mr. Adeson Yorinde, can you say something?
Yeah, I think with regards to the third hypothesis, what the third hypothesis is saying is that hello.
Yeah, we can hear you. We can hear you.
Yeah, what the third hypothesis is trying to say is that what it's saying is that the two factors are not that means the two factor variables, they're not actually exerting effect on the continuous variable. Let's assume we are looking at sex and occupation.
Exactly.
What is saying as regards income, what we are saying is that as a male and somebody who does not have a job, what it's saying is that this does not make your income to be different
from another person who possibly is a female but has a job.
Yes.
Yeah, exactly. So it means that they don't interact. Because if they do interact, the effect of their interaction will definitely be apparent on the outcome variable. And so that is what that hypothesis is testing. It's saying that there is no significant relationship between the interaction of the two factor variables and the dependent variable. And so let's look at how that hypothesis is tested. You have sorry, okay, you can do a box plot here. A box plot for income, sex, and occupation. And of course, let's have an idea of how that is. You have female and clerical. Okay, you have female clerical, female management, female order, female professional, female sales, female service. Okay, these ones are male clerical, male management, male order. So that we can really understand what this box plot is really talking about. So yeah, where you can see that some of them are high, some of them are low, some of them are low. So you see some element of differences really, but then we need to see what direction that is exactly by going further to doing a test, an ANOVA test, and of course a follow-up test, which is a test of separation of means. So like I did earlier on, this is your ANOVA, and you have your summary here. I don't know why the summary is not showing. ANOVA, another ANOVA. No, it's also not showing. That's something's wrong somewhere. That's let me get it up, please. Around from beginning again. Supposed to show. I'm going to install it. So okay. Okay. Well, it's on. That's a good thing. But I don't know. We need to supposed to be bringing in the summaries. So something's wrong somewhere. So let me close it and open it back. Sometimes some of these things will. Okay, so this 1 minute, I'll be back. I don't know what's the problem. Okay. Sorry for the okay. Okay. I don't know what the problem is. To run normally. It's running. Okay. So it's the same way. The only thing is okay, I think yeah, it should run, it's running. The only thing is I will not, but I'll be able to show this result here. Let me make this income 2. From 2. Yeah. So it's the same thing. I can show the results here. Okay. So this is the results here.
So
Yeah.
yeah, but the print function you wrote is supposed to print on the screen, but it doesn't print any result on the script there, or on the console. Why is that?
Yeah, there is I don't know what the problem is, but the good thing is the commands were executed. Sometimes it happens I will have to shut down my R completely, then refresh it, come back, then it starts working better. So I guess that was what I needed to do, but the time is not there. So, but what I've done is I've gone to the file directory to go and bring the result that was generated. You can see that the result was actually generated using the commands. Yeah, look at the time here. The time result was generated 10:48. This was 10:49. So it ran and it executed. Yeah. So what we would have seen in the console is exactly what I'm showing us here in the Word document, which is saying that yes, for sex, there is also significant relationship between sex and income, just like occupation as well, and it's significant even at 0.0%. Now, sex interacting with occupation is also significant. That one is significant at 0.01%. So let's look at other distribution, other analysis. We look at other analysis, you will be able to make sense of it. Look at this. You have income for female that are clerical officers, management, order. So it's comparing them. I mean, it's pairing them. Female clerical is income, female management is income. If you look at this income distribution, you discover that male in management cadre have the highest level of income, followed by professionals. Okay, followed by female professionals as well, followed by female management. I mean, male management followed by female management. And so you have that, but you cannot still decide whether or not, I mean, to say it is significant. So you need to come to this separation of means. This separation of means is a bit complex, but then that's the only thing you could use to make a decision as to whether there's significant difference actually, but which one is higher than the other. You discover that this table is arranged in order of magnitude of their income. You have the highest to the top most and the least to the bottom. Okay, and you have this distribution. You have your alphabet. If you anywhere you have the same alphabet, if you have the same alphabet with any subgroup, for example, M professional and M management, they are not significantly higher than each other at 5%. However, these two, they are significantly higher than F professional. Okay, and F professional is also not significantly higher than M sales and F management. Just like the two are also not significantly higher than the other, and of course they belong in the same category with M order. And so that's the way you interpret it to be able to make sense of the data at the end of the day. So once you're able to master what this alphabet means, which means that if you have any group that carries the same alphabet with another group, that means they belong to the same category. They are not significantly higher than each other, at least at 5% level of significance. And so that's what this table is saying. We may need to read further on how to interpret an LSD analysis, maybe at the end of this class, to be able to connect better with what I am trying to say here. For the purpose of our time, we may not want to spend longer time than we have done on that part. And so this will mark the end of today's class. But in order to help us, I've been able to come up with two exercises. One clearly defined, and the other one is not so defined. The first one says that we should use the iris data set in R to run a one-way ANOVA for separate length, separate width, better length, and better width, each by factor variable species. Okay, we can easily do that. Then number two is that we check some other data frames in R and run some two-way ANOVA analysis. We run some two-way ANOVA analysis. Okay, so that is the end of the class, at least from me. We have about 6 more minutes, within which I think I will have to entertain one or two questions before we eventually wrap it up for today. Thank you.
Yes, sir. Hello, sir.
Hello, yes, sir. I'm here.
Yeah, I have two questions, sir. Number one is on your assignment, for the one on iris data. I said we should run. You know, some of those data they have NA. Do you want us to omit the NA and work with the
that omit NA?
Okay. So number two is that I would like to ask the kind of test to use. For me, I am a civil engineer, and we normally work. I work with construction materials, like trying to mix, sand, cement in different proportion, and we can try to do replacement of maybe cement. If we say cement is like 50%, then we say, okay, let's take 30% of the cement, then 20% we can look for another material in which we can use to replace cement. Then we try to vary the material and see how the I don't know if there's the type of test we can use. And they are all going to be like I don't know, what should I call it? Should I call it categorical or like factor? But what I'm trying to say is that we can have the gravel that we know, we have the sand, we have the cement, which are the three things that make up a concrete.
Okay, sorry, if I may comment. Are you talking in the context of a research, or you are talking in the
Yes, I'm
context
talking of in the context of a research now, like that. If I want to do an analysis and I have my cement, and let's say I now divided the cement into two parts, then I look for another material to substitute the second part of the cement. If I don't want to use the cement as a whole, then I look for another material to substitute for the cement. I can now vary the material with the cement in like 10%, 20%, 30%, and see the effect on the output of the concrete. So I don't know if there's any kind of test that I can use for something like that.
Okay, I think that looks like you may want to consider a two-way ANOVA, because you are looking at different categories of different treatments, and
Yes.
also different level of inclusion. Okay, that's the sense I can make of the scenario you just printed, different treatments, and maybe you're also varying the quantity of
Yes,
of
I have to vary quantity.
yeah. It looks like you are not dealing with just one factor variable here. You are dealing with
Yes.
at least two factors. So you may want to consider. But let me also maintain that you didn't paint the scenario appropriately. So I understand that, yes, maybe it's an idea that you're trying to still cook up.
No, it's not an idea. What I'm trying to say, okay, let me explain very well. Is we have three things that make up a concrete. We have the cement, the gravel, and the sand, which they have their own proportion. Let's say, for an example now, the gravel has 50%, the sand has.
So you have different inclusion level. You vary,
Yes.
you vary
Yes.
content. Very gravel, you vary cement, you vary
No,
sand.
I'm not varying everything.
Isn't it?
I'm not varying everything. Let's just say the gravel has 50%, the sand has 30%, and the cement has 20%. So because of the emission that is in cement, that it emits CO2, and people are trying to reduce the content of the cement in concrete, they now have to look for materials to replace the 20% of the cement. Let's say we look for fly ash. So we now say, okay, the 20% of the cement, let us try to see if we can put 5% inside the 20% of the cement. Let us give cement 15%. Let us use 5% of fly ash. So let us see if it will affect. Then they first create a control with that 20% of the cement. Let's say when they create the control and they try to test for the strength of the concrete.
Yeah, Mr. Abidemi, please, can you do this for me, please? Yeah.
Yes.
You know what we do? You can always reach out to any one of us that has taken you one aspect of this series at any point in time. So please, maybe after this class, you can privately engage me. I will be more than happy to answer your questions. The time is really not there. This is 11 o'clock already, and also I'm aware that some persons may also be asking me one question or the other. So, but you can, in fact, you may explain it in maybe in form of writing.
Yes.
Just send it.
It
can even be on WhatsApp. So I'll be more than happy to make it. Yeah, thank you.
Yes, thank you.
So,
okay, yes, you have the floor, please.
Yes, please. Thank you for this lecture. It's been very indicative. But I have this issue with ANOVA, because, like the results you presented, there's always this issue I have with interpreting it sometimes. Like, let's say it says that variable A is different, it's quite different from variable B. That's variable A is not equal to variable B. But then it also says that variable A is same as C and variable B is same as C. So sometimes it's very difficult to explain. How can you say that A is not equal to B, but both A and B are equal to C? I don't understand what I'm saying, sir.
I do. Yeah. I perfectly understand what you are saying. What I can say here is sometimes Duncan or LSD may not be the perfect post-hoc option you may want to consider. For some situations that come with such complexities, you may want to also run some other post-hoc that are simpler. Okay, that comes like pairing them to say, okay, this compare with this is better. This compare with this is better. That can make your interpretation of some of those results simple. That's one. Two is if you followed me, if you followed my explanation of the result that I also generated, if you followed me, you discover that I was also okay. For example, if you say okay, A, they are the same, B, they are the same, or B is significantly different from M order. I mean, F professional is significantly different. So sometimes if you are not very careful, you may not really be able to make full sense of this data. You may want to consider another post-hoc test to be able to, especially those ones that compare across the different categories. I mean, you can use that to complement whatever this is saying to be able to get your result better into them. Okay.
Okay, sir. Please, could you be more specific? Which post-hoc tests can solve this kind of problem, please?
Okay. You may want to consider Tukey, okay, or Bomberoni. Yeah, you can try Bomberoni and Tukey. I think Bomberoni and Tukey can do some pairwise comparison. Yeah, Bomberoni. So I was also going to bring in Bomberoni into this script, but because of the time that we have, that's very short, I didn't bring it eventually. But Bomberoni can do some perfect, some pairing, and that can sort out some of these issues of difficulties in explaining some of these things that we're talking about here.
Okay, sir. Then that means, like, for instance, now it's already a different question now, but similar. Before we run ANOVA, we have to clean the data. Like this assignment you gave now about iris data sets, we have to do a whole lot of cleaning because there will be lots of outliers. So everything must be cleaned, and we ensure that we have the same sample size across various groups and all. So we must do all this, or we run it the way, because the way you run your analysis, you didn't clean the data, and I don't know if this makes your the results valid, or I don't know. Do we have to go through the whole process of data cleaning?
Some data really do. It's not in every situation that you clean data. Some data are clean, although because we've done data cleaning before now, we've done a lot of work on data wrangling. I didn't consider that aspect of. I mean, that's an important aspect of this class today, and that's why we didn't bother, because data wrangling alone takes so much time. And so, but in a real-time analysis scenario, you need to do a whole lot of things. You need to, for example, run some summary statistics to be able to determine outlier cases, and using appropriate procedure to ensure that those outliers are treated as appropriately as possible before you eventually proceed into the final stage of your work, which is the analysis. Before you do analysis at all, I mean, there are some data wrangling and data processing activities that must really go into your activities before you eventually do the last part of the work, which is data analysis here. Thank you. So any other questions?
Hello, sir.
Hello, yeah.
Yes, sir. Thank you for the lecture, sir. I still want to go back to this separation of mean, and in the case where you want to I want to believe that if you have to go to use Bonferroni, it means that probably when you are separated using LSD or Duncan multiple range test, then you are doubtful about the stringency of probably a particular set of data, and you actually want to ascertain that, okay, if it is carrying the BC to show that they are not significantly different from each other, you now want to confirm if truly they are not different from each other, and that is what will take you to Bonferroni, or you are just doing it neutrally because you want to not really understand what the LSD and the Duncan multiple range test are trying to pick from that data. I just want to be clear on that. Do you go to Bonferroni because you want to be more stringent, or just because you want a clarity with the separation of the means?
No, yeah. Why I was trying to say that was because sometimes if you run just one, you may not be able to adequately speak to that data, interpret the data. Sometimes the result comes with some level of complexity. But I just admitted now that there is a way some of these different options that we have complement each other. And so sometimes when you have a Duncan multiple range test that would essentially be presented almost exactly the way LSD is presented here today, you may want to compare that with a Pamperoni that will give you an idea of peer by peer cases in such a way that you can determine for each of the peers that each of the peers that you have in your analysis. And so essentially what I was trying to say is that you could choose some some post-hoc options that will be able to complement the ones that we possibly selected that possibly you found it difficult to interpret adequately. So they serve some complementary roles to each other, and they help us to be able to draw better conclusion and make better decisions about our analysis. That was exactly what I was trying to
Okay,
say.
sir. Okay, sir. Thank you, sir.
Yeah, you're welcome. Okay, so on that note, I think this is 10 minutes passing the hour of 11 already. It's been a long day. I want to appreciate every one of you for making inputs and for staying till the end of the class. It's been a wonderful time. I enjoyed the feedbacks particularly and also the questions. And like I also remarked, anyone who has any question, possibly you have any issue that you possibly want us to deal with, or possibly you need some clarifications about, we'll be more than happy to attend to any of the questions. You can do that by mailing us. Of course, the admin of this platform will refer those questions to the most appropriate person based on the classes we have handled before. Once again, I want to appreciate everyone. Thank you very much.